Tonight could do that. He did that, so it's gonna
It's part of the reason I don't want to go back out there. There's one stupid that you don't find in a lot of places.
You ain't gonna live forever anyway.
Yeah, but I'd rather not burn to death.
No, burning is not a good thing.
That's not my purpose.
Shot you back in the head when a Joe 30 and about 110, that would be a good way to do it.
All right, go ahead. What was your question?
Oh, it was number 6. It says,
Read it to me.
suppose that a mercury barometer is taken to the summit of Mount Everest, where the atmospheric pressure is exactly 1/3 that of sea level. If mercury has a density of 13,500 kilograms per meter cubed, what will be the difference in the mercury height in the closed end and open end of the barometer?
Okay, well, we didn't really talk about barometers, but we'll do it now. If you look at a mercury barometer, this is, well, in chemistry, you guys have those ones upstairs, right?
Yep.
And they usually consist of a little, like a little reservoir. And then there's a tube down here that's placed into the reservoir with an open end. And then that tube goes up and it has kind of a closed end up here. And this tube's evacuated, so that means there's vacuum in here. And, you know, there's mercury here. And then up here, there's mercury. So, the idea is that at any given point, like maybe right here, the pressure in the fluid's going to be the same. So that means that the pressure here at the surface of the fluid in this reservoir is atmospheric pressure because it's exposed directly to the atmosphere. But as I move over and right in this tube, right under this tube, this mercury at this level is not exposed to the atmosphere. But it is, and so all the pressure is caused by the weight of mercury above it. Okay, and so at 1 atmosphere, this would be, anyone know what atmospheric pressure is in terms of millimeters of mercury?
1.01 e to the 5.
That's what it is in Pascal.
Pascal.
What?
760.
Yeah, so this would be 760 millimeters of
Millimeters of
mercury.
mercury.
And you get, well,
Oh.
okay, let's go back and see how we get that. So 1 atmosphere is equal to, what was it,
7.
well, it's 1.01 10 to the 5th pascals. And this is a Newton per meter squared. And so that is equal to rho G times the height or of the mercury above the ground. The pressure at some depth of mercury. And if I plug in them, and so if I wanted to get what this H is,
H equals
1.01 times 10 to the 5th pascals divided by rho G. And rho is this, G is 9.8.
Okay.
And if I do that, I should get 760. Is that what you get?
Yeah. Oh, I got a 0.76.
I thought you do.
Is that right?
0.76,
So I do meters.
0 meters.
Okay.
Okay,
Okay.
760 millimeters.
Okay. And then, do you do the same thing with 1/3 of?
Yeah, that's right. So if I took it up to
Atmosphere.
Mount Everest,
It's
I wouldn't have 1 atmosphere, I'd have 1/3 of an atmosphere. So it'd be like that.
Okay.
And so that would tell you how much.
You got like 0.25, and so then you just subtract it to find the difference, because it asks for the difference in height.
Okay.
Right.
I didn't know, I thought, what was it again?
It says that if mercury has a density of that, it will be, what will be the difference in the mercury height in the closed end and open end of the barometer?
Yeah, so this is the open end, this is the closed end. So this is, the height of mercury is at it'd be 760. The difference in heights between those is 760.
minus whatever.
So it's just 760 at atmosphere. And 760 over 3 at 1/3 of the atmosphere.
What's the difference?
That's just the difference in ends is just the height.
Um,
Yeah.
can you do one like the U-shaped one? Like in the book?
U-shaped one. Well, it's the same
Is
thing
that the
there.
same thing?
Yeah, same thing here. Instead of having a reservoir like here, you just have an end that's open and an end that's,
Okay.
end that's open here and exposed to atmosphere. And then, this end is closed.
Mhm.
And so
So
the
that-
pressure here has to be the pressure here at the same height of the fluid has to be the same as the pressure here. And if this end is closed, that means the atmospheric pressure has to be due to all that mercury that's up here. Okay?
So
Makes
that
sense?
end, the closed end doesn't move, right?
The closed end, yeah, this is a vacuum up here. The only pressure is due to the weight of the mercury up there.
Okay. So like even if you start at this level and then go up to Mount Everest, that line still stays the same. The only thing.
No, this one will move.
Oh.
Because the pressure here and the pressure up here will be the same. So this one will probably go up a little bit because there's less atmospheric pressure, and then this one will go down a little bit, so that the difference in here would be the times density times G. The difference in height here and here would be 1 atmosphere, or whatever the atmospheric pressure is.
The vacuum in there is what's holding it in.
Yeah, there's a vacuum, well, it's not, yeah, there's a vacuum up here, and so all the pressure at this height and this height of mercury would have to be the same.
So it's the same principle as an airlock.
What's that?
So like for brewing, you use an airlock, it's the same principle.
Yeah.
We're using liquid to.
Yeah, that's right. So this is the same pressure at any given height if it's at rest. And we'll see that from Bernoulli equation in just a second. And if it's the same pressure, then here all the pressure at this surface is due to atmosphere because it's just exposed to atmosphere. Here, the pressure is due to the fact that it's some depth inside mercury. Okay. So you just figure out what that depth is.
So the closed is 760.
You're dropping your fluid, creating more space, which makes more vacuum.
So the only reason the vacuum sucks things up is because of the other end, where it's really, you're really pushing things in, is the atmosphere. There's no just force from the vacuum. It's the atmospheric pressure at this end that tends to push things upwards. That's a lot of, it can be a lot because there's a, it's 14 pounds of PSI for the Earth's wow. All right, you ready to go work on Bernoulli's equation and stuff? Barometer can be thought of as an application of this. All right, so what did we derive yesterday? We derived something called Bernoulli's equation. And what was it?
Got 1/2 rho v squared plus u plus rho g h equals the other one, that was 2, and then the equals.
Yeah, this is the same everywhere
Yeah.
inside the fluid. So it's a constant everywhere inside the fluid. And so this tells us some interesting things. I'll do a couple of examples. So let's consider a lake being held back by a dam. So I'm gonna look at the cross section of the dam. So this dam's gonna look like this. And then there's a reservoir back here. Now dams usually have an intake, kind of a tube. You have a tower usually, and then an intake that goes through here, through, you know, maybe a turbine or something at this end. Anyway, you got a tube that goes out the other side of the dam. And you can use the water flowing through over at this end to generate electricity, or if you want, all sorts of things like that. All right. Let's say that the height is just 100 meters. And that's the height above, you know, this level of the tube at the other end. What's the velocity of the water in this pipe here? Or the speed of this water in this pipe? So this is an application of Bernoulli's equation. This thing has to be the same everywhere. So what I'm going to do is I'm going to take this point, 1, and this point, 2. And I'm just going to write this out for both those points, and then plug in numbers. So, at point 1, I have 1/2 rho V1 squared plus pressure 1 plus rho GH1. That has to equal 1/2 density V2 plus pressure 2 plus rho GH2. I'll call this height H equals 0. Only difference in heights will really matter. So first of all, at point 1, is the water moving? If it's at top of the lake? Probably not. So I can put a 0 here. Pressure 1 and pressure 2, are these, it's both atmospheric pressure, isn't it? Because they're both exposed to the atmosphere.
So you can cancel that.
So I can subtract atmosphere from both sides, atmospheric pressure from both sides. And just cancel those out. What's height 2?
0.
0. So this is 0. All right, and so I'm left with rho GH1 is equal to 1/2 rho V2 squared. I can divide through by the density, and I get that 2 multiplied through by 2, I get 2GH1 is equal to V2 squared. Or V2 is the square root of 2GH. So how much is that if I plug this in here? This is not 2V, this is just point. So how much was that?
1960?
44.27.
Square root that?
Oh, no.
What's that?
44.27.
44.27 meters per second. All right, so that is, you know, it's 2.2 meters per second for every miles per hour. So that's about 90 or close to 100 miles an hour coming out of this end. Water flow, so that's pretty impressive. You can use that to do a lot of work. But you see what I did? Very simple. By the way, with the, as you can see here, say this wasn't a lake made up of liquid water. Say you're making a dam on some, you know, moon Triton, and it's made out of liquid methane, different density fluid, liquid. Does it matter?
No.
Yeah, the density canceled out, which is kind of good. All right, so, makes sense? You want to do another example?
Yeah.
Okay. All right, let's say I have a pipe full of liquid. Here's some liquid. And I'm trying to go get through a pipe. And so on this end, I put an extra pressure on the pipe. The total pressure would be 1.6 times 10 to the 5th pascals. And this ends up 5 meters. What would be the speed of the water coming out of there?
What's the height there? 0?
Yeah. So this is just 5 meters above this point. Okay. I'll let you guys work on that. What's that? How about I give you a minute or two and then I'll race you. And then I'll race you. Let's just say you attach it to a reservoir. So the water's just flowing into it. All right, I'm gonna race you guys now. You guys good? Okay, who got it?
I have an answer.
All right. What do you guys get?
14.8 meters per second.
I got 11.
I got 14.7. Is that what everyone got?
No, I got 11.3.
Should I go through it?
Yes, please.
Okay. So I'm going to call this point 1, this point 2. Now, and then I'm just going to write that this at point 1 is equal to this at point 2. So 1/2 rho V1 squared plus pressure at point 1 plus rho VH1 is equal to 1/2 rho V2 squared plus the pressure at point 2 plus rho VH2. Okay? H2, I'm going to take that as 0.
Velocity is also 0.
Velocity at point 2, 0?
No, 0.1.
Right. So this is 0. What's the pressure here?
1.6.
That's 10 to the 5th, and then this was
5 meters.
5 meters, 1,000. Water. I guess I assume this is water.
49.
So yeah, 1,000 times kilograms per meter squared or cubed.
Why can't you not cancel the densities out in this case?
What do you mean?
Because they're
Because I
different.
have pressure.
Oh, if you have a pressure.
The densities, you can't pull density out.
So I have 2 pressures.
Yeah.
Yeah.
So how do I cancel out the densities? So if I divide the whole thing by density, it's just dividing the pressure. Yeah. So I have to divide the pressure by density too. And then
Yeah.
divide by density.
Oh, okay.
So just don't.
All right. So I get pressure 1 plus rho VH1 is equal to 1/2 rho V2 squared plus pressure 2. Could subtract pressure 2 from both sides. So pressure 1 minus pressure 2 plus rho VH1 is equal to 1/2 rho V2 squared. Running that over. And so that pressure 1 minus pressure 2, that's 0.59 times 10 to the 5th Pascal, plus rho GH is 1,000 kilograms per meter cubed, times 9.8 meters per second squared, times H1, which is 5 meters. And that was equal to 1/2 rho V2 squared multiply both sides by 2, and divide both sides by rho, which is 1,000, and take the square root. Yeah. And that's the, when I did that, I got, you know, the 14.69. Something like that. I guess seven pretty much. Say 1.6 times 10 to the 5th, subtract 1.01. See what I did?
Huh?
No, 1,000, that's
Same.
still 1,000.
Yeah.
Still 1,000. You ready to do another one? All Okay. This next one's kind of an interesting device. Okay. All right. Okay, so sometimes you get situations where you want to measure the fluid flow velocity in a pipe. And it's kind of, but you don't really want to, I mean, but how do you do that? You know, you can put little there is a simple way to do that. And one way to do that is to just put a little extra tiny little pipe here that's connected and then open to some known pressure, like atmospheric pressure. Sometimes, a lot of times you'll have a known, what we call a pressure gradient, there's a difference in pressure between two sides. We're going to try and avoid that complication. And you just have a little extra tube here and you measure this height. Okay. So let's see if we can figure out how that height would be related to the velocity flow in that pipe. We'll assume that this is at atmospheric pressure, and right there, this end may be at atmospheric pressure too. It'd be helpful if we knew all the pressures, but we'll make it as simple as possible.
So the one above it is ATM also?
This is also at atmospheric pressure. Just for whatever reason, the velocity is flowing like this. I guess probably this would be a little bit above atmospheric pressure, and this end would probably be at atmospheric pressure. But we won't worry too much about that.
So would you left it as if it were at 1 atmosphere?
I'll tell you what, just to make sure that we get it more correct, we'll do this as 1.2 times 10 to the 5th pascals. And this here is 1.0 times 10 to the 5th pascals. How about that? Okay. Give it some numbers. So this V, by the way, so this is P atmosphere, roughly. And the V should be the same at that point in the pipe. So I'm going to treat this as 0.1, and I'm going to treat this as 0.2. Okay? And then I'm going to apply Bernoulli's equation, which was conveniently erased. So I have 1/2 rho V squared plus P plus rho V H is equal to constant everywhere in the fluid. So I'm just going to write that out for this 0.1. I'm just going to write that out and set that equal to that for part 2. So I get 1/2 rho V1 squared plus P1 plus rho V H1 is equal to 1/2 rho density V2 squared plus P2 plus rho V H2.
So we're technically trying to find V1 then?
Well, we're trying to relate this H with the V in the pipe.
So it doesn't really matter what that pressure is because we could do the same thing. The velocity would just be a little different, right?
Which one?
Yeah.
Yeah. This one, it wouldn't matter, but you need to have one pipe end open to atmosphere. Okay, and take one where the pipe end is the atmosphere, is this one.
Okay.
Or at least a known pressure. Okay, let's see. Okay, so at 0.1, this is not 0. This is P at, what's this?
Yeah.
P atmosphere, right? And maybe I should take, what should I do with H1?
H1, H0.
Yeah, let's call this H equals 0. There. Good. So, 0. All right, and what about V2?
B2 is not moving.
Yeah, you have a little pipe that's actually perpendicular to where it was going. It shouldn't be moving there. So we just go to 0 here. P atmosphere, right? Like that. And then this, we'll just call that H2H. Yeah, we can subtract P atmospheres from both sides of this equation. Cancel that out. So I'll rewrite it at this point. So we have 1/2 rho V1 squared is equal to rho VH. What can I do now?
I cancel row.
I
Cancel
can
the
divide
rows.
through the rows, and actually I get V1 is equal to 2VH square root. Or I could just relate the H to the V1 squared, so I get H is equal to 1V1 squared over 2G. So by measuring this height, I automatically know what this B is. Pretty cool when you don't want to have to go in there and, I don't know, put a paddle wheel in. I don't know how else you do it. It'd be there are various ways, but it'd be complicated. Just put a little clear tube there, right in the pipe, and just make you see how high it is.
So when there's a lower pressure or a lower velocity, does it shrink? The height
Yep, that's right.
shrinks?
So the height goes like this. So if I put 1/4 or half the velocity here, I get 1/4 of the height. calibrate that. That makes sense to you guys? Yeah, they have old flow meters that do that. Kind of more modern flow meters like in gas pumps and stuff like that. Slightly different. They use a little membrane that they make the fluid flow over and it vibrates and they look at the vibration frequency. But that's more complicated. What's that? What's that one?
Like a water meter.
They might do that on bigger ones, but I think the gas pumps vibrate. That's what I've heard.
I know, well, like your water meter in your house, out in the little hole in your yard, that's just a little propeller thing that spins in there.
That makes sense. All right. How about pumping up water from deep underground? This is the last application for any of these capable of doing. There's a bunch of other ones. By the way, what are you doing tomorrow?
Question.
Questions.
So please come up with questions and find a group, come up with questions. Because we're going to have our exam review tomorrow. Okay.
Can you give us an example from each part two again?
From what?
Like from each chapter?
A question from each section of the, like you did last
We can
time.
do that.
So is this the last like concept you're covering?
Yeah. Well, there's one other. Maybe I should do that. This one's very, very simple. But well, it's maybe not that. All right. Okay, let's say that I have a pipe that narrows down. Okay. So I call this area of cross-section area of the wider of one part of the pipe A1, area 1. And let's say this is speed V1. And let's say that this area is an area A2. And here I have a speed V2. Okay. I want to see what the relation between these are, the V's are. And the thing about an incompressible fluid is that the amount per time that goes past any given cross-section of the pipe has to be the same everywhere. So that means the same amount of fluid per time has to be going across here as over here. Otherwise, I'd be building up fluid somewhere, like in here. And if it's an incompressible fluid and that pipe's full, that's possible. So the rate of fluid flow is the same across any cross-section of the pipe. I can figure out what the rate is. So let's say that I have a V1, I take a distance V1 here. Then in this time t is a distance, it's a velocity, speed times a time, right?
Mm-hmm.
And this is V1, we'll say. So in time t, all the fluid inside of here will cross this area. The volume of that fluid would be A1 V1 t, right? So the volume per time would be A1 V1.
Volume.
Let's say in that same pipe,
Area times.
in that same time, all the fluid in a distance V2t crosses this cross-section of pipe. So this V2, the volume 2, here would be V2T, A2, and the volume per time would be V2, A2. If the flow rate's the same, this over time has to equal that over time. So this just gives us an equation that's A1, E1, is equal to A2, V2. And this is the relation between area of cross-sectional area of a pipe and flow velocity in the pipe, if I narrow it down. Does that make sense? All
Makes
right.
sense.
So we're going to do one example of that.
Wait, the volume's the same?
The
Oh, no.
volume per time going across a cross-sectional area has to be the same as
Oh,
for
okay.
this area
And that
this
area.
area.
Okay.
Otherwise, the fluid is building up somewhere for
Okay.
an incompressible liquid.
So basically, if you have the velocity for your bigger tube, you can divide it by A2, and that'll give you the velocity for your smaller tube.
Divide, multiplied by A2,
A2.
divide by the ratio, or multiplied by the ratio A1 over A2.
Okay.
V2, V1, or V2.
Exactly. All right, so an example of this is to get high-speed jets of water. You know, they even use high-speed jets of water to machine steel. You ever seen this?
To what?
Machines still like cut off steel.
Yeah, like it's, I mean, you can get this going pretty fast. Let's say that I created some nozzle. By the way, the shape of these nozzles, with this narrow end of the pipe, what they're made out of is very tricky. Yeah, they do it fancy ceramics, diamond, I think, for the high pressure ones, or at least coated. Things like this. Let's say that I have a pipe that really narrows down. Let's say my flow velocity here is like 10 meters per second. And this radius here, let's say is 5 centimeters. Okay, how narrow would I have to make this nozzle? What's the radius of this nozzle? In order to get a flow speed at the end of here of 300 meters per second. So see if you can do that.
Wait,
What's the area of a circle?
what's
2 pi
5 centimeter? Is that the height?
5 centimeters is the radius
Oh,
of
the
this,
radius, okay.
of this bigger section of pipe.
And then,
Flow velocity in this bigger section is 10 meters per second. And then I have a little, and then it narrows down into a nozzle or a narrower section of pipe. And I want the flow velocity in this narrow section to be 300 meters per second. Can you get the radius of this nozzle?
wait, do we treat these as like circles or
Yeah.
spheres? Circles?
Treated this cross-section area to be a circle.
Okay.
You ever heard of water hammer? You ever worked with like big pipes and stuff with water hammer? No. You ever heard of water hammer? Have you ever had troubles with it? Have you ever run into troubles with it?
So much, 50 around to, Western Australia.
Yeah, man, you have to pump and stuff down just to replace the valves, so we don't have a little pressure thing. And do you get it?
I got the area, but I don't know how you get the radius out of the area.
Pi r squared.
I know, but like, going backwards.
22.
Like, divide.
3.
Oh, it's like, okay,
Yeah,
so
like,
that's what I see.
About
Alright.
0.009
That's what I
And then take the square root.
0.009.
Okay.
So 9.
No, 0.9. 0.9 millimeters.
137.
I got
9 millimeters. Okay.
It's 0.9.
Okay.
Or, wait,
I did it.
no, it's not. 0.9 centimeters, yeah. 9
So
millimeters.
9.9 centimeters? Oh, sorry. Okay, so 9 millimeters.
Yeah.
Okay, is that what you guys got? Okay, let's go ahead and check this out. So this one, I'm gonna call this R1, so this R2. So I have pi R1 squared, that's A1, right? Times velocity 1, which was 10 meters per second, is equal to pi R2 squared
It's 2 pi r.
times 300 meters per second. So I'm going to cancel out the pi's,
Pi r squared is the
divide both
area.
sides. Does this make sense, by the way, by doing pi r squared here? That's
Yeah.
the cross-sectional area of a pipe. It's a circular pipe. Okay, then I divide through by R1 squared over, oh, I'm trying to solve for R2, aren't I?
Mm-hmm.
So I'm just going to divide by 300 meters per second. Cancel. And then take the square root. So I get R2 is equal to R1, because I can bring this out of the square root and turn it into just R1. Square root of 1 over 30. This ratio of 10 over 300. So this square root of 1/30th, anyway, it's, what would that be? Square root of 1/30th? So R2, 5 centimeters. So this will be a little bit less than 1/5.